Okay, let's get into stuff for 6.3. 6.3 is about equivalence relations, and equivalence relations are very, very important in mathematics. So what I'd like to do is look at this definition, and in the book they actually talk about the equivalence mod some number. They give an example, but I'd like to go a little bit further with that, and we can actually show that the relation equivalent mod some number, we'll call it n. We can show that that's actually an equivalence relation. All we need to do, right, to show something's an equivalence relation is to show that it's reflexive, symmetric, and transitive, right? So if you remember those properties if I have some set S, right, and I have like something A, so for all A in S, right, A is related to itself, right? So this is goodness. This is the reflexive property, right? I want to show it's symmetric, right? So for all A and B and S, right, if A is related to B, right, then B is related to A. Right. And finally, I want to show the transitive property for all A, B, and C in S, my set, A is related to B, right, and B is related to A, or I'm sorry, B is related to C, right, then A is related to C. And so let's take a look at, well, I mean, when we're having numbers mod something, let's look and see what we can think about that, right? So for two numbers, right, so if A is congruent to B, we'll say mod in, right? Another way we can think of this is that A minus B is some multiple of n, right? We'll call it k, right? Basically, I mean, I guess I could put there exists some integer k, right? There exists some integer k such that, right, A minus B is equal to that integer times n, right? So the modulus, basically, right? So let's see if we can use this sort of definition, right? This definition right here. Maybe we can use this to our advantage to actually show that the congruence mod n is an equivalence relation, right? Or the equivalence mod n. So I want to show, right, for reflexive, right? Remember what I want to show is that A is congruent to itself, mod n. And you might think that this is trivial, and I guess in a way it kind of is, but, right, let's use our definition, right? So, you know, I mean, let A be, you know, A is going to be an integer, right? Suppose A is some integer value, right? And consider, right, A minus A, right? Well, A minus A, that's equal to 0, right? And I can actually say that that's equal to 0 times some value, some integer value n, right? So that implies that right, that A is in fact congruent to itself, mod n. Okay. Let's look at the symmetric property. Remember, what we want to do here is we want to suppose, right, just like we've done in previous times, we want to suppose that A is congruent to B, right? Right. So, right, we want to show that if A is congruent to B mod n, then B is congruent to A. So on, right? Well, this is just a direct proof. I'm going to suppose this is true, right? Remember, we can just imagine if P then Q, this is my P, this is my Q. I'll just suppose P is true. So, suppose that A is congruent to B mod n. Right? By our second definition of congruence, mod n, or I guess equivalence, however you want to say it, I can say that this implies that A minus B is equal to, right, we'll call it some value K times n. Right. Now consider B minus A. Right? Well, B minus A, right, if I could like rearrange this, right, if I put the A in front, I've got negative A plus B, right, I could say that that's actually equal to A minus B. Right? Now, what do I know based on the equality that I established earlier is that negative, negative, right, A minus B, I can just say that that's equal to a negative K times n, right, like this, if you want, doesn't really matter. So if I distribute that through, what I'll get is that B minus A is actually equal to negative K times n, right? So haven't I found an integer, right? An integer value times n, right? Well, this implies that B is congruent to A, right? Mod n. Right? And this is what I wanted to show. Now for transitivity. Right? This is where if A is equivalent to B and B is equivalent to C, then A is equivalent to C. Right? So first, right, and you notice the way that that's actually set up, right? I've got, right, we'll say A equivalent to B, and we'll say B is equivalent to C mod n, right? Right. Notice we have this and, right? Both of these are true, right? Then A is congruent to C. Right. So this whole thing, right? This is just, direct proof time. Right. This is an easy way to do it. Right. I'll just suppose that my P is true, and I'll deduce that Q is true. Right. Right. I just suppose that this hypothesis part is true, right? The first part is true. And then use something to actually deduce the other things. Right? So if I suppose they're true, right? A is congruent to B, right? And right, B is congruent to C. Right. So what does this mean? Well, I can use my other definition, right? That means that a minus b is equal to k, right? We'll say k1 times n, right? And in this case, we could say b minus c, right, is equal to k1, k2 times n. Right? And something that I can do actually is define b in terms of something else if I really want. And by that I mean, let's take for instance this thing right here. Well, if I move c over, right, then I get an expression for b in terms of c, right? Then b is equal to c, we'll say plus k2n, right? This is once again an equivalent way of actually writing equivalence mod n, right? So b is equal to c plus some value k, we're calling it k2 times n. So notice I have an expression for b over here. I can just substitute it into this, right? Right. So let's notice what I'm going to get. I've got a minus b is equal to k1 times n. By substitution, I'll get a minus, right? I've got c plus, this is k2n, is equal to k1 times n, right? I guess I should, whoop. I guess I should be doing implications here. So notice here, I'll distribute that through. I've got a minus c minus k2n is equal to k1n, and hopefully you can see where this is going, right? Because what I want to get at the end is that a minus c is equal to some integer value times n, right? So let's see if we can do that. So if I move that over, I'll get a minus c, right? I'll get k1, k1n, right, plus k2n. Right. And so a minus c is equal to k1 plus k2, and then the n is going to be on the other side. Now what do I know is true about this? I know that this is an integer value, right? Because k1 and k2 are both integers, and we know that the integers are closed under addition, right? So the sum of two integers is going to give me an integer. So I know that the value k1 plus k2 is an integer. So in fact, I have found an integer value, right, k1 plus k2, that gives me, the difference of a and c is equal to an integer times my modulus n, right? So, right, this implies that a is actually congruent to c mod n, right? And, this is really important. One thing that's kind of nice is that the equivalence, right, mod n, well, what it does is it creates these things called equivalence classes, right? A common way that we might see these equivalence classes written is I could have some z, right? I can have some value n, right? So I can have some n times z, right? And I could have some n times z plus 1 all the way up to n z plus, right? And we'll call this n minus 1, right? So these are what are referred to as equivalence classes mod n, right? And if something is in this equivalence class, right, so like things are in, let's say, in z plus 1, all of the values in z plus 1 in this set, right, they're going to be equivalent. Right? Now, another nice thing that the equivalence classes, in this case for mod, do is they partition the integers, right? And I think that there's a definition in the book about partitioning. All this really means is that the union of these sets, right? So in this case, the union of in z plus 1 all the way up to in z plus n minus 1, right? So this entire thing, right, this is going to give me what's called, the entire initial set, right? So the union of all of these is going to give me the integers, right? And the intersection of any of the sets, right, is the empty set, right? So if I intersect in z and in z plus 1, right, there are no common elements between those sets, right? Same with any other sets, right? So the union of all the sets is the integers, right? So I could write that, let's call this, group of equivalence relations. Let's call this set S, right? And so S is, it's a set. I mean, it's a finite set where there are, let's say, n elements in it, right? Now, all of the n elements are infinite size, but that's really not important for us. So we could define this to be a set S, right, where, this is a member of S, right? This is a member. And what I could say is that the union, right, of the S, right, this is going to equal Z, right, the integers, and that, right, the intersection, I'll say the intersection of all S, we could do S there, intersection of all of the S's, maybe SI would be better, who knows. The intersection of all of the S's is actually the empty set. Right. And this is what it means to create a partition. If I partition a set, the union of all of the sort of like other sets I've created out of the partition, right, it divides it up nicely, right? If you imagine that you have a set, right, like this, and I partition it in this way, right, where I have these sort of chunks, right? So here's some, right, I'll call S1, here's an S2, here's an S3, here's an S4, right? Notice that the union of all of these, maybe this gives me my big set, right? I don't know what I want to call the big set, P maybe. So, right, these, all the little divisions, right, they're sort of discrete divisions, like things don't exist in any of them, right? So something in S1 is not in S2, right, and vice versa. So things in S2 are not in S3, not in S4, right? They sort of form these very strict places. Okay. All right. Right, so the union is going to give me the original set there, right? But the intersection is going to give me an empty set, right? They have no elements in common. So that was a fun thing. The last thing I'd like to do is talk a little bit about this. This sort of comes out of nowhere in this chapter. They're talking about graph isomorphisms, and there's an exercise. The 4 examples of graph above actually are two pairs of isomorphic graph. Which pairs are isomorphic? So there's an idea of what's called isomorphism. Specifically graph isomorphisms. The word isomorphism comes up pretty frequently in mathematics, especially in higher level mathematics. The idea of having an isomorphism is something we'll want to. It's very important, right? An isomorphism is actually it's a function from one graph to another. It takes what are called well, it takes the points, right, on a particular graph, right? So like let's say these points, right, and it maps them to points on another graph. And it also preserves what's called an edge endpoint relationship. So if I called this point 1, right, and this point down here 2, and let's say I map it to another graph where 1 and 2 are not in the same place, well, 1 and 2 have to have this 1-2 line running between them, right? There has to be a line that goes from 1 to 2 or from 2 to 1 or how. I mean, this is not a digraph, so the direction does not matter in this particular case. It's an undirected graph. But that's basically what I want, right? So something that is going to be true about isomorphisms for graphs is that if I look at another graph, it's going to have the same number of edges and it's going to have the same number of points, right? Because I have to preserve what's called an edge endpoint relationship between there. There are things called graph homomorphisms, which don't necessarily need, that doesn't need to be true, but we won't talk about that. One thing we can do is to kind of look at, well, here, this one has 2 and this one over here has 2, right? Notice that this one goes to itself, right? This one is quite an eccentric path, but it does still go to itself, right? And there's these 3 things connecting the 2 dots. So notice that I actually have the same thing, right? Now, which of these is which is not important, right? Once again, this is a bit of an eccentric path right there, but you know, it still gets the job done. So I still have these two nodes on the graph, right? And they're connected by 3, right? There's 3 lines. And I have one node on the graph that sort of loops back onto itself, right? So in fact, in some ways, right, these graphs are the same, right? Isomorphism is really a measure of sameness on graphs in this case. Right. Likewise, if I look over here, I've got 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. And if I want to kind of look at what's happening, even though maybe this is not, it doesn't look the same, right? These graphs are really very similar, right? Because, look, I've got this one, right? We could, let's say, call this one here, right? Well, it goes to this, right? And it goes to this. Well, this one goes here, and it also goes here. Right? Right, and then these 2 are connected, right, together. Right? So we can think of that. This one goes here, right, here. Could imagine that there's this big arch here, right? And so on. So you notice that there's really, these graphs are the same graph, right? And they're same up to some arrangement, right? So these 2 are the same, right? And then I'll draw a dotted line around this one and this one to show that these 2 are the same, right? So this pair is the same, this pair is the same, right? In a sort of like same shapeness, right? So there we go. And